In Chapter 2, we really create the framework for describing how a soil and water live together. And so how does water sit in soils? And we start by defining a soil-water system, and we really need to identify the three phases that are in the system. And so that's going to be the solid phase, the liquid phase, and the gas phase. And we have to parenthetically say there's a biological phase. So now we've defined our phases. The interesting thing is we have the problem of how big a sample is a sample. Because as we go to the grain size, all we have is either solid or void. And so we have to spend a fair bit of effort to say how big a sample do we need to have to be able to actually say that we've characterized a soil. And this is typically called the REV, the representative elementary volume. So now we have a sample. What do we measure in that sample? So one of the most important things, of course, is going to be the liquid content or the water content. And here we identify that there's two basic frameworks we could use. We could use the weight of it, the gravimetric, or the volumetric, the volumetric fraction of water versus total volume. So now we have quantified these things. We know how big a sample to get. Now we have to understand the physics of it. What's going on here? And so the energy state of water is really a big issue. And we have lots of contributors to the energy state of water. We have, of course, the capillary pressure, which is going to largely come from surface tension. Then we also have the osmotic component of the energy, where it's the dissolution of solutes into the water. We can also have the dipole interaction with the solid. So the water is dipole, solid's dipole, we have a dipole interaction, and other interactions, energies. And so we have to go through a very careful analysis of which energetic terms come up and what they mean. We then go a little bit more into surface tension than anything else, because surface tension is the force that really dictates the amount of water and the flow of water under kind of normal conditions. Many of these, like the osmotic potential, does not really drive flow, but surface tension, which gives rise to the capillary potential, really drives flow. And the key point here is that we have that the capillary pressure generated by surface tension is equal to minus 2 sigma over r, where we see that the surface tension of the liquid and the radius of the capillary of the spaces really dictates the surface tension. So this is pressure versus geometry, really tying liquids and solids together for the first time. With that framework, then we can start to say what happens when you have a complex soil where you have a water content versus pressure curve, and this we call the characteristic curves, and we really identify how this all ties together from a physical point of view. Finally, you have to actually get parameter values for all these things, and so we spend a fair bit of time looking at the measurement methods, both in the lab and the field. So what we have at the end of the day is a framework for describing the state of water and soil together, and how the changes in water content are reflected in changes in pressure, and how the basic features of the soil give rise to the basic physics of that water-solid interaction.